In this video, we'll be discussing section 6.3 from chapter 6 of P4, and we'll be discussing integration by substitution. Okay, so back in P3, we did learn how to use the reverse chain rule in integration. We learned the chain rule in differentiation. Okay, we learned the reverse chain rule for integration. Okay, so let's say that if you have the integral of root of 2x plus 5, okay, if you have the integral of root of 2x plus 5 the whole raised to x, the whole with respect to x, you're integrating this. Okay, in that case you can use the chain rule. Okay, in this case notice that the derivative of this function is going to be a constant. So if you have the derivative as a simple constant, in that case you can easily integrate this. Okay, if you have the derivative as a simple constant, in that case you can integrate this. This will become 2x plus 5 the whole raised to 3 by 2 divided by 3 by 2 excuse me, 2x plus 5 the whole raised to 3 by 2 divided by 3 by 2, and then you divide by the derivative of the function inside the bracket. So inside the function you have the derivative as 2. Okay, and here we have we can divide the entire thing by 2. Okay, and then we have the plus c, the constant of integration. Okay, plus c. Now if this thing does not work out if the derivative of the function inside is not a constant. So let's say that if you have the integral of the root of 2x squared plus 5, okay, if you have the integral of the root of 2x squared plus 5, in that case we cannot write that this is equal to 2x squared plus 5 the whole raised to 3 by 2 by 3 by 2, okay, and into 1 by 4x, because 4x is the derivative of the function inside the bracket. We cannot write that this is 1 by 4x. Okay, this is not a constant. Okay, so in this case this is definitely not right. Okay, we do need the x over here. Okay, at least, I mean the 4 can also be there, but let's say that if instead we have 3x into the root of 2x squared plus 5, 3x into the root of 2x squared plus 5 the whole with respect to x, and if we want to integrate this, in that case we can now continue with that integration into 2x squared plus 5 the whole raised to 3 by 2 divided by 3 by 2. Okay, now 2x squared plus 5 needs 4x as the derivative. Over here you have only 3x, therefore this is going to be into 3 by 4. Okay, because we need 4x over here. Notice that 2x squared plus 5 needs 4x over here. So since we have 3x, we are multiplying the entire answer by 3 by 4. Okay, so if you have a constant as the derivative of the function inside the numerator, inside the function, in that case you can easily divide by the constant. But if you have a function, in that case definitely you cannot use the reverse chain rule as it is. You do need that function, okay, in the integrand itself. Okay, we did learn this back in P3. Now let's say that instead you have a more complex function such as the integral of x squared into root of 2x squared plus 5 the whole with respect to x. Okay, in this case notice that 2x squared plus 5 has got derivative 4x. Okay, and over here it is not 4x, it is x squared. Okay, so you could multiply by 4 and then divide the whole thing by 4, but even then this thing is not the exact derivative of the function inside. Okay, so often in these cases we can use some other advanced integration methods. In this section we'll be learning how to do integration by substitution. Okay, so in the first question that we'll be trying to solve as an example, we'll be doing example 6a. Example 6a. Example 6 part A. Okay, and this is on page number 74, and you're given to find the integral of x into root of 2x plus 5. Okay, so this is actually similar to what you had over here, and it is not similar, excuse me, it is not similar to what you had over here, because over here you had 2x squared plus 5, here you have 2x plus 5. Okay, so notice that over here 2x plus 5 is the derivative of the function inside is going to be simply 2, but over here we have x. Okay, so definitely this is not following your regular reverse chain rule that we learned in P3. Okay, so over here we are asked to solve this using the substitution u. For the first part, we are using the substitution u equals to x plus 5. Okay, so we are going to use the substitution u equals to x plus 5, okay, to help us solve this integration, to help us find the answer to this integration. So the first step to continue with this substitution procedure is that notice that we have got 2x plus 5. In place of 2x plus 5 we can easily substitute u, but over here for x we do need something in terms of u. So the first step is to rearrange this if required. Okay, so if we rearrange this, we get u minus 5 the whole by 2 is equal to x. Okay, so now if we substitute this, we get the integral from, you can substitute for x u minus 5 by 2. Okay, then you have the root of 2x plus 5, and 2x plus 5 is equal to u. You can substitute x back into this and you'll get the answer is equal to u, but over here since we have the relationship given to us already, just use that instead of trying to do the long procedure of substituting x into the expression. You can use u is equal to x plus 5, so this becomes root of u, or root of u can be written as u raised to half. Okay, now we are not done yet with the substitution. We have dx over here. Okay, and dx, since we are converting everything to u, we need to convert dx to du. Okay, and you can easily convert dx to du by differentiating our relationship given to us. Okay, the substitution given to us. So let's differentiate this relationship that we have, okay, on both sides with respect to x. So we get du by dx is equal to, differentiate 2x plus 5 with respect to x, you get 2. Okay, so du by dx is equal to 2. Then take dx to the other side, take 2 to this side, and you get half du is equal to dx. Half du is equal to dx. So you can substitute dx by half du. Okay, so overall we get this expression over here. Okay, notice everything needs to be substituted. Okay, if you're doing a substitution, everything in x needs to be substituted with your variable of substitution. In this case we have u. Okay, so everything needs to be substituted along with the dx. Okay, so now we have the substitution done. Let's continue the integration. It is going to be simple integration over here. We need to simplify the expression. Notice we have a half, we have a by 2. These are constants, so you can take the entire thing out. You can write this as 1 by 4. Okay, into the integral. Okay, now we have over here du remains the same, so du just copies down. Okay, and over here we have left this part. Let's multiply it out. So u times u raised to half is going to be u raised to 3 by 2 minus 5 into u raised to half is going to be 5 into u raised to half as usual. Okay, now we can integrate this, and this becomes 1 by 4 the whole into u raised to 5 by 2 by 5 by 2 minus 5 u raised to 3 by 2 by 3 by 2, and don't forget the constant of integration for indefinite integration, because over here you don't have limits, we do need the plus c. Okay, now we are done with the integration. Since we are done with the integration, we can simplify the expression. So let's simplify it. For the first one you get 1 by 10, so u raised to 5 by 2 by 10. For the second one you get 5 by 6 of u raised to 3 by 2. Okay, plus c. So we are done with the integration, but notice that our question is in terms of x. Okay, and we did a substitution for u. Therefore we do need to reverse the change, okay, and we need to replace u with its equivalent in x, okay. So the substitution helped us find the answer, but the final answer should not be expressed in terms of u. It needs to be expressed still in terms of x. So substitute 2x plus 5 in place of u. You get 2x plus 5 the whole raised to 5 by 2 by 10 minus 5 into 2x plus 5 the whole raised to 3 by 2 by 6 plus c. Okay, so this is your final answer. And you can leave it over here unless the question asks you to simplify the expression even further. Over here the question is not asking us to simplify the expression any further, so we can leave it over here, and this is our answer. Okay, now let's consider, okay, in this first example we substituted u equals to x plus 5. Okay, let's do the same problem and try to use the substitution, okay, as in part B. Okay, in part B they're asking us to solve the same integral, but you're going to use the substitution u square is equal to 2x plus 5. In the previous case we did u equals to x plus 5. Okay, so if I have u square equals to x plus 5, we do need something for x, so let's rearrange this. We get x is equal to u square minus 5 by 2. Okay, x equals u square minus 5 by 2, so you can substitute u square minus 5 by 2. Root of 2x plus 5 becomes the root of this expression, so that is going to be root of u square, which is simply u. Okay, u. Now we do have dx also needs to be substituted. Okay, let's differentiate this. Okay, if you differentiate this, you get differentiate both sides with respect to x, so this one becomes 2u into du by dx. Okay, be careful with what you're differentiating with respect to. Okay, we are differentiating with respect to x. If it was simply differentiating with respect to u, it would be simply 2u, but over here since you're differentiating with respect to x, we have an inner function u and an outer function square, so the outer function gets differentiated first, 2u, and then you multiply by the derivative of the inner function u, that is du by dx. So this is equal to differentiating the right hand side with respect to x, you get 2. Okay, now let's simplify this. We need an expression for dx, so let's simplify. 2 and 2 cancel out, we get u du is equal to dx. Okay, so u du is equal to dx, therefore we can in place of du we are dx, in place of dx we are going to substitute u du. So this, okay, notice that this comes from the x, this becomes the u, and this dx becomes the u du. Okay, now the rest is going to be simply integrating it as usual. So we have, I can take out the half from and make it a constant for the whole integral we have here, and then let's multiply. The du remains the same as usual. Let's multiply the u throughout, so we have u and u square times u square minus 5, that becomes u raised to 4 minus 5u square. Okay, u raised to 4 minus 5u square. Now we can integrate this, you get half, u raised to 4 becomes u raised to 5 by 5, 5u square becomes 5u cube by 3, the whole plus c. Okay, simplifying the expression, we get u raised to 5 by 10 minus 5u raised to 3 by 6 plus c. Now even though you're done with the integration, the final answer needs to be in terms of x, so we need to reverse the substitution. Notice that u square is equal to x plus 5. Here you have u raised to 5. Okay, u raised to 5 is the same as u square the whole raised to 5 by 2. Okay, this is P1 mathematics. Okay, and u raised to 5 is equal to u square the whole raised to 5 by 2, and u cube is the same as u square the whole raised to 3 by 2. Okay, so substituting them back, we get this is equal to 2x plus 5 the whole raised to 5 by 2 by 10 minus 5 2x plus 5 the whole raised to 3 by 2 by 6 plus c. Okay, Now notice that in this case also you get the same answer as in the previous case, but okay, depending upon our substitution, in the previous case we used this substitution u equals to x plus 5, and by using this, even though you were able to integrate it, notice that integration was actually a bit difficult because it had got half powers in it, 3 by 2 half, and they got integrated to 5 by 2 and 3 by 2. Okay, and there were some fractions over here which were complex. Over here, using u square equals to x plus 5, okay, gave us whole powers 4 and 2. Okay, and we did not have fractions to deal with. Okay, so definitely depending on your substitution, sometimes using all substitutions will work as long as you can integrate it. Okay, but some substitutions might be easier. Okay, they might make your problem even more easier than other substitutions. Okay, but there is no particular rule that you need to use this kind of substitution or some other kind of substitution to make your integration easier. Okay, sometimes some substitutions which are easier in one case might actually be difficult in some other cases. Okay, so there is no specific rule that you need to use this substitution in all cases. Okay, or some other kind of substitution in all cases. Usually it all depends on the case in question. Okay, and depending upon the case, your substitution could be different. Okay, now usually in P4 you will be often given what substitution to use, so you do not have to worry about that, but only in the most simplest of cases you'll be left to determine the substitution to be used. Okay, now let's consider our next example. The next example we'll be doing is example 7, and over here we are given to find the integral of cos x into sin x into 1 plus sin x the whole cube, 1 plus sin x the whole cube with respect to x. Cos x into sin x into 1 plus sin x the whole cube with respect to x, and we are asked to find the derivative, we are asked to use the substitution u is equal to sin x plus 1. Okay, u is equal to sin x plus 1 to solve this integral. Okay, now first thing, notice that u is equal to sin x plus 1, so you can easily substitute that over here for sin x plus 1. Okay, now for sin x we can easily substitute, u minus 1. For cos x though, okay, we might have to use the identity cos squared x equals 1 minus sin squared x. So cos x is equal to root of 1 minus sin squared x, okay, which becomes root of 1 minus u minus 1 the whole square. Okay, now the thing is, even though cos x is equal to root of 1 minus u minus 1 the whole square, the whole root, okay, usually you'll not be you'll be given questions where the substitution is going to make your integration easier. Over here, notice that this root is not going to make your substitution easier. Okay, your processing easier. Okay, if you try to substitute this over here, it will become even more complex because you have this root over here, okay, to deal with. Okay, and usually because the substitution that will be given in P4, okay, will be such that it will make your problem easier. Okay, right now it does not look that way, and that is because we do have another thing to evaluate, dx. Okay, so often the trick lies over here in dx. Okay, dx might actually help simplify your answer. So let's find out what dx is. Okay, dx you can find from u sin x equal u equals sin x plus 1. Differentiate both sides with respect to x. We get u becomes du by dx. Sin x plus 1 becomes cos x. Okay, differentiate sin x with respect to x, you get cos x. Now what is dx then? Take dx to the other side, you get du is equal to cos x dx. Okay, du is equal to cos x dx, and the trick is over here. Notice that dx actually has this expression over here. Okay, dx has cos x in it. In other words, cos x and dx, this two can simplify to give you du, and thus you do not have to worry about this root. Okay, you do not have to worry about this root. This root, you do not make the substitution, because this is definitely going to make your processing even more difficult. So the trick often lies in the expression for du and dx. Okay, that might actually sometimes simplify your answer. So we here notice that du equals cos x dx. So this entire thing we can substitute with du. Okay, now continuing with the integration, we have, first let's substitute. Sin x is u minus 1. 1 plus sin x the whole cube becomes, 1 plus sin x the whole cube becomes u cube, and then cos x dx becomes t. And this is definitely much easier to solve, okay, from the first expression, and also without if you try to substitute this, okay, definitely it will not be easier to solve. Over here right now you do have a very simple expression to integrate. Okay, now the rest is going to be simple integrations. Expand the bracket, you get u raised to 4 minus u cube the whole with respect to u. Okay, and that becomes u raised to 5 by 5 minus u raised to 4 by 4 plus c. Now back, you need to substitute u back, okay, so that is sin x plus 1. Okay, so this is going to be equal to sin x plus 1 the whole raised to 5 by 5 minus sin x plus 1 the whole raised to 4 by 4 plus c. And that's your answer to this question. Okay, now one thing, let's say that if you're unsure that, okay, did I make any mistakes in this procedure, okay, while trying to substitute all this stuff over here, okay, and you're unsure whether your answer is correct or not, in that case you can usually do the check by differentiating it back. Okay, if you differentiate it back, you should get the same answer. If you do not get the same answer, definitely you have done some mistake over here. Okay, so we'll not be doing the check over here, okay, but definitely in an examination, if you do get the time, okay, because definitely if you try to differentiate this back, it will take some time. If you do get the time, okay, while you revise your answers, in that case you can differentiate it back to see whether your answer is correct. Okay, now let's consider another example. In this example we'll be doing example 8 from page 76. Okay, example 8 from page 76, and we have the first question. A part is the integral from 0 till 2 for x into x plus 1 the whole cube with respect to x. Okay, and you're not given the substitution. We are not given the substitution over here, so we can, if you're not given the substitution, in that case you have the freedom to choose what substitution you want to use. Okay, if you are given the substitution, in that case, great, you can use the substitution that has been given. Okay, so over here, let's say that you want to use a substitution. Whenever you try to use substitutions, you need to simplify. Okay, the aim should be to simplify the expression. So over here, let's simplify this x plus 1. Okay, and therefore let u equal x plus 1. Okay, so u equals x plus 1, so I can substitute x plus 1 with u. What about x though? X can be substituted as u minus 1. Okay, so I can substitute for x u minus 1. Now what about dx? Okay, differentiate this with respect to x, you get du by dx is equal to 1, and therefore du is equal to dx. So I can substitute dx with du. Okay, now one thing more though, in the previous two examples, in the previous three examples actually, okay, we were doing in the previous three examples we were doing indefinite integration. We did not have any limits. Okay, over here so we did not have any limits. Over here, and thus we had plus c. In this case we are having definite integration because we do have limits. Okay, and the limits also need to get changed. If x is getting substituted with u, okay, dx is getting substituted with du, the limits also need to get changed, because these limits over here are going to work only for x. These are the x limits. We do need to replace them with the u limits. Okay, so when x is equal to 0, the lower limit is 0, okay, u is going to be equal to 0 plus 1, which is 1. And when x is equal to 2, u is going to be equal to 2 plus 1, which is 3. Okay, so basically use the substitution, okay, to find your new limits. Okay, now rewriting this entire thing, we get from 0 till 2 becomes from 1 till 3. X becomes u minus 1. X plus 1 the whole cube becomes u cube, and dx becomes du. Okay, so everything is replaced, substituted. Now the rest is going to be simple integration. We can integrate from 1 till 3 for u raised to 4 minus u cube the whole with respect to u, and that now becomes u raised to 5 by 5 minus u raised to 4 by 4 plus there is no plus c over here. Okay, so notice that in the previous examples when we were doing indefinite integration, our final answer needed to be in terms of x. Therefore, we substituted u back with the expression in x. Over here, our final answer is not going to be in terms of x. It is going to be a simple number because it is definite integration. So you're not going to have something in terms of x. You're going to have a numerical answer. Okay, so the numerical answer is going to be the same irrespective of whether you use u or try to convert u back to x and then substitute the x limits. Okay, so in both the cases you'll get the same answer. So we'll try both of the methods. Okay, let's say that we try to convert this into the x version, the x version. So in that case, the x version is going to be substitute u with x plus 1, so that becomes x plus 1 the whole raised to 5 by 5 minus x plus 1 the whole raised to 4 by 4. Okay, the whole. Notice that this time the limits are not 1 and 3 because we are having x over here. It is going to be the x limits 0 and 2. Okay, x limits 0 and 2. So this one, if you evaluate it, substitute 2, you get 3 raised to 5 by 5. Substitute 2, you get 3 raised to 4 by 4. Substitute 0, you get 1 raised to 5 by 5. Substitute 0 into this one, you get 1 raised to 4 by 4, and this is what you get. On the other hand, okay, you could substitute 1 and 3 into this expression as well, and you get the same thing. Substitute 3 for the first one, you get 3 raised to 5 by 5 minus 3 raised to 4 by 4. Substitute 1 into for the second part, you get 1 raised to 5 1 by 5 by 1 minus 4. So in both the cases you're getting the same answer. Okay, so again in definite integration, once you get this stage, you don't have to change it back to x, because you could do that. It is not that it is not correct. You could do that, but that is basically adding one more step, and we could substitute the limits over here directly without having to worry. Just make sure that these limits are the u limits, not the x limits. Okay, the x limits only apply for x. The u limits apply for u. Okay, and you'll get the same answer irrespective of whether you do the substitution for u or the insertion for u or the insertion for x. Okay, so this is the answer. You can simplify this, and this is going to become 3 raised to 5 is 243 minus 1 is 242 by 5 minus, simplify this by expanding the bracket. You can do it in steps or you can use the calculator. So this is 81 minus 80, that is going to be 80, and that over is 20, and over all this simplifies to 142 by 5. Okay, so this is the final answer, 142 by 5, 28.4. Yeah, makes sense. Alright, now let's consider the next example. Over here we have the integral from 0 till pi by 2 for cos x into root of 1 plus sin x the whole with respect to x. Okay, cos x into root of 1 plus sin x the whole with respect to x. Again, we are not given the substitution, so we do have the freedom to choose the substitution we want to use. Okay, let's use the expression. Let's see, if we use u equals 1 plus sin x, what happens? If you use u equals 1 plus sin x, in that case 1 plus sin x gets replaced by u. What about dx? Okay, you can differentiate, you can get du by dx is equal to 1 plus, cos x simply. Okay, du by dx is going to be cos x, the derivative 1 is 0, sin x becomes cos x, and therefore du is equal to cos x dx. In other words, cos x and dx together becomes du. Okay. On the other hand, okay, let's say that instead of using u equals 1 plus sin x, if you want to use u square equals 1 plus sin x, what happens? In that case, if u square equals 1 plus sin x, in that case this becomes u. Okay. Now what happens when you differentiate this? You get 2u du by dx is equal to cos x. Okay, so differentiate this, you get 2u du by dx, differentiate this, you get cos x, and you get 2u du is equal to cos x dx. Okay, so cos x dx will get replaced by 2u du. Okay, so you could use either of these substitutions, it does not matter. Okay, in both of them, as long as you work the method out correctly, both the substitutions are going to give you the same answer. Okay, so for the first method we do need the limits as well. Okay, so for the first method, when x is 0, okay, when x is 0, the lower limit is 0, what is u? U is equal to 1 plus sine of 0, that is 1. When x equals pi by 2, u equals 1 plus sine of pi by 2, okay, which is 2 overall. Okay, make sure that this pi by 2 is in radians. In integration, in differentiation, trigonometry is always going to use radians. If you use the second version, if you use the second substitution, in that case, when x equals 0, u will become 1 plus sine 0, which is again 1. The whole root is 1. But when x equals pi by 2, this will become 1 plus sine 0, 1 plus sine of pi by 2, which is 2, the whole root. Okay, so this is square, so therefore this is going to be u equals root of 2. Okay, so this, okay, if you use the first substitution, you get the integral from the new limits are going to be 1 and 2, so the integral from 1 till 2 for cos x dx becomes du. Okay, and 1 plus sine x becomes u, so u root, or in other words u raised to half. So you could do the first substitution, or you could do the second substitution. The second substitution, if you use, in that case the limits are going to be 1 and root 2, so 1 and root 2. Okay, and in this case root of 1 plus sine x, root of 1 plus sine x becomes root of u square, that is simply u, and then dx, cos x dx gets replaced by 2u du, so this cos x dx will become 2u du. Okay, in case this is confusing, let's replace the u with v so that this is not confusing. So this is v, so in this case we have v, v still looks similar to u though. But, okay, so the first substitution u, it will become u raised to 3 by 2 by 3 by 2, and if you simplify this, you'll get u raised to 3 by 2 by 3 by 2 will become 2 by 3, that okay, u raised to 3 by 2 from 1 till 2, okay, and that will become 2 by 3 of 2 raised to 3 by 2 minus 1 raised to 3 by 2, which is 1. Okay, and this overall simplifies to become 2 by 3 into 2 root 2 minus 1. On the other hand, this one, if you simplify, if you evaluate this, you get 2v square with respect to v, 2v square with respect to v. Okay, so that becomes the integral. Okay, so 2v square with respect to v becomes 2v cube by 3, 2v cube by 3 from 0, not 0, 1, excuse me, 1 till root 2. Okay, 1 till root 2. So that will simplify to substitute root 2, you get 2 by 3 into root 2 the whole cube minus 1 the whole cube, which is 1, and that again leaves you back to the same answer. So in both the cases you get the same answer. Okay, so it does not matter what the substitution you use is, as long as you can work out through the substitution and get to the final answer. Okay, both the substitutions, any substitution is going to be acceptable. Alright, now let's consider another example, and in this example we'll be doing 4C from exercise 6C. From exercise 6 we'll be doing question number 4C, okay, on page 77, and we have over here the integral from 0 till pi by 2 for sine of 2 theta divided by 1 plus cos theta with respect to theta. Okay, sine of 2 theta divided by 1 plus cos theta with respect to theta, and we are not given the substitution. We are given the freedom to choose the substitution we want to use. Okay, so again, notice that if we want to simplify this expression, we can start with 1 plus cos theta. So let's replace the entire 1 plus cos theta with something. Okay, so let u equal 1 plus cos theta. Okay, so if u equals 1 plus cos theta, in that case this entire denominator will get simplified. Now what about d theta? Okay, this, if you differentiate, you get du by d theta. Du by d theta becomes, differentiate u, you get du by d theta. Differentiate this expression, you get minus sin theta. Or in other words, if you rearrange this, you get du is equal to minus sin theta d theta, minus sin theta d theta. Okay, now notice that 1 plus cos theta can easily replace with u. Okay, but we do not have sin theta, we have sin 2 theta d theta. So this, we cannot simply replace the sin 2 theta d theta with du. Okay, we do need sin theta. Okay, so notice that we have sin 2 theta, and we can expand this. Okay, so we get the integral from 0 to pi by 2. We are not yet substituting, so the limits are still the same, 0 to pi by 2. Okay, and this becomes sin 2 theta is going to become 2 sin theta cos theta, 2 sin theta cos theta divided by 1 plus cos theta, the whole with respect to theta. Okay, now our substitution is going to be easier. Okay, because 1 plus cos theta becomes u. Sin theta d theta minus sin theta d theta is equal to du. Okay, in other words, minus du is equal to sin theta d theta. Okay, I just transferred the minus to the other side. Okay, so sin theta d theta is going to be minus du. So this part over here, minus sin theta and d theta, is going to be replaced by minus du. What is left is the cos theta here. Okay, because everything has got substituted, we do need to substitute the cos theta, and that cos theta you can easily find from the first expression. Cos theta is equal to u minus 1. Okay, so with everything done, we still have one more step before we continue the substitution, and that is the limits. Okay, do not forget the limits. So the limits over here are 0 and pi by 2. So if theta equals pi by 2, in that case u is equal to 1 plus cos of pi by 2. Cos of pi by 2 is 0, so therefore u is equal to 1. When theta is equal to 0, in that case you have 1 plus cos of 0, that is 1 plus 2, which is going to be 2. Okay, now continuing with our substitution, theta equals pi by 2, u equals 1, so the upper limit is 1. Theta equals 0, u equals 2. So when theta equals 0, u equals 2, the lower limit is 2. Now usually, notice again a word of caution over here. Okay, be careful with what you're substituting, which value substituting with which value. Okay, usually when you do integration, the lower limit is going to be smaller than the higher limit, but that is not a fixed rule in integration. Okay, but whatever is the upper limit should always be the upper limit. So pi by 2 over here is u equals 1, so that is the upper limit here, and 0 is the lower limit, and that becomes u equals 2. Okay, so it does not matter, the lower limit could be larger than the upper limit. Okay, but the upper limit is always the upper limit. The upper limit, you cannot just make the upper limit be the lower limit. Okay, the lower limit can be larger than the upper limit though. Now continuing, the 2 does not get changed, so we have 2. The sine theta d theta becomes minus du. Okay, the sine theta d theta becomes minus du from here. Okay, the cos theta becomes u minus 1. And finally, we have 1 plus cos theta. That 1 plus cos theta becomes u. Alright, now continuing, we can notice that we have the minus as a coefficient. So this minus, we can take it out as a minus, or okay, minus of this entire thing. Okay, if we apply minus to the entire thing, the signs of the limits will flip out, but let's just not worry about that part right now. Let's just, so the minus is now the coefficient here, the minus comes out, the limits are unchanged. Okay, and therefore we have multiply this entire thing out, you get 2 minus 2 by u, the whole with respect to u. Again, 2u minus 2 the whole by u is going to be 2 minus 2 by u with respect to u. Now you can easily integrate both of these parts. The first expression was definitely much more complex. Over here we have a very simple expression to integrate. This becomes 2 becomes 2u, minus 2u becomes minus 2 ln of u modulus. Okay, the whole from 2 till 1. Do not forget the minus sign over there. Okay, so this is going to be the once you've done the integration, this is the answer, this is the stage you reach. And now the minus copies down, we have in the bracket substitute 1, we get 2 minus 2 ln 1 modulus. 1 modulus is going to be 1. Okay, so when you substitute 1 modulus, you get 2 ln 1 minus, for the 2 when you substitute, you get 4 minus 2 ln of 2 modulus. 2 modulus is again 2, so you can easily neglect the modulus symbol. Continuing, we have minus, let the minus still stay the same. 2 minus 4 is going to be minus 2. ln 1 is 0. ln 1 is 0, so this thing cancels out. We get minus of 2 ln 2 becomes plus 2 ln 2. Now apply the minus, you get 2 ln 2 minus 1.